everyone, so my name is Kathy and today I'm going to show you a very simple way to make what is known as a Cartesian diver. As we can see here, I have all the material I need for today. It's very simple. Here we have a large bottle, so this is going to be our container, and here are the material that we need to make the floater. So here we have the bottle that we're going to use to make the floater, and here is a hairpin that I will use to act as a weight, and I'm going to attach the hairpin to the bottle. The reason for this is that this bottle is made of plastic and the density of it is lighter. It's lighter than water. So I want to add this weight here to make the average density of this floater to be just slightly heavier than water so that we can make the floater work. Now I'm going to attach the hairpin to the plastic bottle using the clear tape or whatever material you can find, as long as you can attach the weight to the bottle, and it's very simple. And here we have the floater. So here we have the floater ready to go. Now we're going to assemble the apparatus. Now the first step is to fill the entire bottle, the larger container, with water. Now you want to make sure that your bottle is filled all the way up to the top so that we can leave as little air as possible. So now we have filled the larger container with water all the way to the top. Here we're going to do the tricky part of this experiment. The tricky part is to fill this floater just right amount of water, leaving the just right amount of air to make this work. Here's where the squeeze bottle come into play. If you don't have a squeeze bottle, you can also use a syringe. Now I'm going to fill this floater with water. So you would want most of the bottle filled, but leaving like this amount of air left so that we can make it float. As you might have noticed, I've marked the level of the water with a Sharpie or a marker. That's because this step might require you to do some trial and error, and it might not work the first time, and if you try enough times, you would eventually get to the right amount. Now I'm going to try with this amount of water. I'm going to cover it with my index finger, invert it, and put it into the bottle. As you can see, the bottle is floating, and you press it down, it's not dropping down. So this means that we don't have enough water in the bottle. Now I'm going to add a bit of several drops of water into the bottle using the squeeze bottle, and I'm going to mark the level again. Now let's try that again. Now you can see that the bottle is dropping down, meaning that you have a bit too much of water in the floater. Because last time the floater was a bit too heavy, now we're going to remove a bit of water from the floater. Okay, so now we're going to try this amount of water and see if it works. Okay, so now you can see that the bottle is floating just about right, so this should be good for our Cartesian diver. And so now you want to cover the bottle, and we're going to try it out. So I've tried 3 different levels of boarding the floater, and hopefully third time is the charm. We're going to try out if it works. So yeah, as you can see, when I squeeze the bottle, the floater is dropping down, and when I release the pressure, it's floating back up. So our experiment worked! The pressure I'm applying to the bottle when I squeeze it compresses the air inside the small bottle, making its density larger, and so it sinks. When I stop squeezing the bottle, the air inside the small bottle expands, and the density is now lower than water, making it float. The experiment of making a Cartesian diver might be simple, but the mechanisms behind can be used to explain how submarines maintain and adjust their depths. When a submarine is on the surface, its tanks are filled with air, and the submarine's average density is less than that of the surrounding water. In order for the submarine to dive, the tanks are flooded with water, while the air is vented out, until its overall density is greater than the surrounding water. To keep the submarine level at a set depth, it maintains a balance of air and water in its tanks, so that its overall density is equal to the surrounding water. When the submarine needs to surface, stored compressed air is injected into the tanks and forces water out. When its overall density becomes less than its surroundings, the submarine rises.